What if the biggest breakthroughs in AI aren't just about smarter models, but about giving them better skills and better research records? In this episode, we dive into two provocative ideas: skill retrieval augmentation, which helps agentic AI find and use the right external capabilities at the right time, and agent-native research artifacts, a new way to preserve the full scientific process instead of flattening it into a PDF. Together, they point to a future where AI can both act more intelligently and learn from research more faithfully. Let's explore the first paper, Skill Retrieval Augmentation for Agentic AI. Skill Retrieval Augmentation for Agentic AI reframes external capability access as a three-stage pipeline: retrieve, incorporate, and apply executable skills from an out-of-context corpus, rather than enumerating them in the prompt. The authors introduce SRA Bench, the first benchmark to decompose this pipeline, with 5,400 capability-intensive instances, 636 manually curated gold skills, and a 26,262 skill corpus, in which only 2.4% are gold. The benchmark spans Theorem QA, Logic Bench, Tool QA, MedCalc Bench, Champ, and BigCode Bench, enabling separate evaluation of skill retrieval, skill incorporation, and downstream task execution across 6 open-weight LLMs, including Quinn, 3, 4B, 32B, 235B, Llama, 3, 1, 8B, Instruct, Llama, 3, 3, 7, 0B, Instruct, and Mistral, small, 3, 1, 2, 4B, Instruct, 2503, plus frontier models GLM-5, 1, and GPT-5, 4 for behavioral analysis, retrieval augmented skills, improved performance over skill-free baselines, and Oracle skill consistently beat direct prompting. On average, Llama 3.370B rose from 47.8% LLM direct to 59.2% with LLM selection, while Quinn 3.32B improved from 53.3% to 62.4%. However, the main bottleneck was not retrieval alone, but skill loading policy. Models often loaded skills at similar rates whether or not the gold skill was present, and they were no more likely to load skills on tasks that actually exceeded native capability. Overall loading rates varied wildly, from 11.1% for Llama 7.0B to 72.1% for Llama 8B. For retrieval, BM25, TF-IDF, BGE, Contriever, hybrid retrieval, and LLM re-ranking were compared. BM25 reached 80.7%. Recall at 10 on Theorem QA, BGE reached 83.4% on Tool QA, and LLM re-ranking was strongest overall. The core conclusion is that SRA is not just a retrieval problem. It requires utility-aware retrieval, relevance-aware incorporation, and need-aware skill invocation. Let's explore the second paper, the last human-written paper agent native research artifacts. The paper argues that conventional PDFs impose 2 loss functions on AI native research: a storytelling tax, which erases failed experiments, rejected hypotheses, and branching exploration, and an engineering tax, which leaves reproduction-critical specifications implicit. To eliminate both, it defines the Agent Native Research Artifact, ARA, a file system protocol with 4 coupled layers: logic, for queryable scientific claims and falsification criteria; SRC for executable code plus full configuration; trace for the exploration DAG, including dead ends and pivots; and evidence for raw outputs that ground every claim. 3 mechanisms operationalize the protocol: a live research manager that continuously extracts structured events from researcher-agent conversations with provenance tags, user, AI suggested, AI executed, user revised, an ARA compiler that converts legacy PDFs, repos into ARA form, and an ARA native review system built around the 3-level ARA seal. On Paperbench and REbench, ARA substantially improves agent performance. Across 450 understanding questions spanning 23 ICML, 2024 papers, and 7 REbench tasks, ARA raises accuracy from 72.4% to 93.7%, plus 21.3 percentage points, and lowers token use from 109 1K to 114 0K. Question overall, with the biggest gain on failure knowledge questions, 81.4% versus 15.7%. On 150 reproduction subtasks across 15 papers, difficulty-weighted success rises from 57.4% to 64.4%. The paper also quantifies the underlying information gap. Only 45.4% of 8,921 paper-bench reproduction requirements are fully specified in PDFs. 26.2% are missing hyperparameters. 20,9% are vague descriptions, and 13.4% are cross-reference only. On RE-Bench, 90.2% of compute cost is spent on failed runs, showing why preserving dead-end traces matters. ARA Seal Level 1 detects all structural defects in mutation tests. Level 2 catches 82.6% of injected rigor failures. Level 3 corresponds to directional reproduction checks. That's a wrap on today's AI paper highlights. Thanks for watching.